Hello everyone, and thanks for having me at the video sim parsing in the wild workshop this year at SCCV 2021. My name is Federico. I'm currently at Bending Spoon after some time at Facebook at Adobe. I just joined this company in Italy. We focus on apps developing, and two of our most important apps are a video editor for iOS and Android, and another app for image enhancement. And so today I'm going to talk about how the challenges of computing semantic segmentation on devices, and I'm going to talk about a method that we developed last year called temporally distributed networks for fast video segmentation. So semantic segmentation is a pillar of the content creator economy. They probably don't know yet, but they don't know it, the creators, but that's what we need. We need to segment images all the time in order to create these effects like these compelling effects like the one that you see on the right. Both of them require foreground background segmentation, for example, in order to add this background, this gradient in one case, pink to azure to light blue. As I said, many effects are based on it. So face enhancing is one, rotoscoping, sky replacement, but in general, all those effects that are that are based on some semantic information. Like, we know that segmentation network heavy, cloud computing would be a solution, which means we stream the video to the cloud. We do the computation, we compute the segmentation maps, and then we send it back to the client, to the phone, to the mobile device in this case. But these negatively impact the user experience, because they are most likely they have to wait a bit at least, or they cannot even do it if their device is not connected to the internet, or most likely they have low bandwidth. So it's gonna take a while, the connection breaks, we lost half of the video, we need to redo it. That's not gonna be entertaining for the users of the app. So best of, there's also the privacy issue, right? Where is the data going, on which cluster, in which region? So of course it's much better to compute everything on the edge device, on the phone. However, of course, there are challenges. One, the hardware is constrained, is small, and it's limited in computational power. And on top of that, battery consumption and overheating are critical, and we cannot afford them. So efficiency is key, of course, in this case. And when I talk about efficiency, model efficiency in this case, of course, we want the inference, not the training, but the inference to be efficient. The first thing we think about is about the architecture design, right? There have been many studies. There have been proposed many mobile architectures that reduce the max while keeping the accuracy. And they don't keep the accuracy, they reduce the accuracy, but they minimize the loss in accuracy. There's always a trade-off, and then it's the decision of understanding what is the sweet point for a particular application on a particular device. Some of the architecture like Squeeze Next, ShuffleNet, MobileNet. Here on the right you can see Squeeze Next. The idea is to have a one-by-one convolution to compress the feature dimensionality before feeding to the 3x3 convolution layer, which are the most expensive to compute. Beyond architectural changes or design choices, there is model compression, which can be done via distillation and quantization. On the right here, this is a figure from GAN compression. The way to do distillation is to have a teacher network which is optimal, which is big, which is trained to convergence, and to distill the knowledge to the smaller student. The smaller student most of the time have the same architecture, but is slimmer. It has less channels, it has less feature dimensions. And so in order to match the dimensionality of the features between the two networks, we add we add a 1x1 convolution. We have some layer, could be a 1x1 convolution, could be a 3x3 convolution to match this, and then we have a distillation loss, which in general could be like an MSE L1, L2 Frobenius norm, since we're talking about tensors. Right, that's great, that's something that helps a lot, and that works on images and videos. But when we use videos, we have like temporal continuity, right? As you see here in this sequence, the content of the video changes slowly, right? First frame, second frame, third frame, they're really similar to each other. And so maybe, actually not maybe, we can, the temporal continuity offers an opportunity to reduce the computation. We do so by exploiting the natural redundancy of the content of consecutive frames in order to recompute only subset of the feature. This is also based on the assumption, which was I'm not sure proven, I would say, that deep layers in the feature hierarchy change more slowly than shallower layers, which makes total sense intuitively, because the shallow layer, they generally capture edges, and edges tend to change abruptly with motion, while deep layer, they capture concept and contextual information, which, for example, here the presence of a horse is not changing over time, or is it changing at a much slower pace than the edges. So the idea is basically to reuse the feature previously computed from a similar frame to reduce the inference computation, while minimizing the loss in the classification accuracy. Now, there is a seminal work, or what I think is a seminal work, which is called Clockwork Convenet for video semantic segmentation from Shellhammer et al. And you can see in this very nice visualization what they're doing is basically they have like some clockwork mechanism that decides when it's time to recompute the features and which features. And so at the first frame, the clockwork says compute all the features. At the second frame, only partial computation. Same for the third frame. At the fourth frame, you know, the horse starts running. There is a big shift in content, and so the clockwork decides to recompute all the features. So this is like the high-level mechanism that enable to reuse like previous features. There are some follow-up works on this. You can see this one, low latency video semantic segmentation. The idea here is to have two different networks, a shallow network called SL here, and SH, which is like the deeper part of the network, and at keyframes, K, K prime, K second, they compute the full feature representation running through the whole network. Then at every frame, they take another network that predicts whether we need to recompute all the features or not. If that's the case, it just goes through the whole network again. Otherwise, it passes the features, the shallow features, through another shallow network, adds on top the logics of the previous frame, and then compute the segmentation. It's interesting. I like the idea. There is only one problem. It optimizes the average latency, but the maximum latency, it's not optimized. The maximum latency, let me go back. Here, you can see it here, it's gonna be the one of the deeper layer, right? Every time we have to recompute a keyframe, we go through the latency of the deep model, which is bad for real-time application, which is not good at all. So last year at CVPR, we proposed a method which called temporal distributed networks for video semantic segmentation, and now I'm going to talk about them. So the idea is simple. Let's imagine we have this network like the A per frame model. This could be any network like DeepLab, PSPNet, whatever. Take an input frame T, encoder gets extract features. Here we have like features of 4 different colors, let's say four-dimensional. We do some dimensionality reduction where we combine these features somehow, and then we get the semantic segmentation. Now, inspired by recent success of group convolutions, which you can see a visualization here, which show that adopting separate convolutional paths can increase a model effectiveness because we enhance the sparsity of filters relationships. So in this case, we have this blue block and we have 2 feature extractor paths through block convolutions that compute separate features, which we then concatenate in the green layer. That's the idea of group convolutions that have been proven to work well. Based on this, we propose something similar. We propose to divide the features from a deep network, like this A per frame model, into groups computed by shallow networks, right? So this is what we call TDNet, temporally distributed model. The idea is that for this case, we split like this big network into 4 shallow networks. Each of these networks compute a part of the feature, which we probably gonna be like based on the distance of that model from the target frame. And then we use a something that we call the attention propagation module, here named APM, to cope for misalignment of the feature, because of course there's going to be some motion anyway between the frames, to mix them up to get a representation of the feature which is similar to the one of the per frame model, and to predict the final semantic segmentation. Now, as you can see in this model, we could also think that the sum of the max of the 4 networks is equivalent. This is probably what we did in the paper, in fact, is equivalent at the max of the per frame model. However, we reuse every time the same features for the previous frames, right? So this is like a sliding window of networks which is sliding over the video frames. So at frame slip +1, as you can see, we only compute TD1, which is 1/4 of the total computation. So that's where the gain is, and that's how we minimize both the average latency and the maximum latency. You can see here, which is different from the previous approach, we never compute the run inference on the full network. So as I was saying, key to this approach is the feature aggregation to cope for the spatial misalignment, which is caused by motion between frames. We tried optical flow. We have an ablation study where we report the performance, and I'm going to talk about it later, but it's expensive to compute, prone to errors, and we didn't get the same accuracy. That's why we propose the attention propagation module, which, as the name suggests, is based on non-local attention, so some non-local mean between feature map and the spatio-temporal feature map, weighted by the similarity that we extract from the encoder. This non-local attention is basically, as I was saying, extended to the temporal dimension. All right, so overall, this is the approach. You see there is an encoding phase. This is easy to explain. We have TD1 extracting featured frames T-3, TD2 frame T-2, etc. So we have all the features, like a part of the feature that we use to compute the frame segmentation of frame T, extracted by this shallow network. However, rather than just generating the value V for the feature map, right, which is like what commonly we do, the encoding extract the feature, what is the value in the, in the context of attention. We also from the encoding extract like the Q, like the query, and the key maps, which are like these orange and violet grids. And they are basically, we use them to build, to create, to not actually to compute and understand the correlations or the affinity between pixels across frames. So as you can see on the top right, the affinity of pixel P with the other frame is equal to the dot product of the Q, the query at frame T, times the key at frame P, P being like T minus 1 or something like this, divided by square root of dk, where dk is basically the number of features, the size of the feature map. So once we do that, we can compute that VT, the new value updated, like once the features are combined, and this is basically the sum of the affinity, like the sum of the values from the previous frames multiplied by the affinity with frame T. This is basically the second equation, and VT prime is basically the final feature map that is then used to compute the segmentation. As you can see, beyond the between like the encoding phase and this segmentation phase, there is like some downsampling layers, and this downsampling layers is basically just some pooling, and we need to reduce the complexity of the feature maps and of basically the self-attention components, query, key, and value, to reduce the computation, to make it efficient. And we'll show later in the ablation study that we don't lose any performance making like by 4, reducing by 4. All right, so details about the training. How do we train this model? Modeling and baselines are initialized with ImageNet, pre-trained parameters, then are trained to convergence like on Cityscape, on Canvid, to achieve best performance. TDNet with M subnetworks, and in most of the experiments we found out 4 to be the right number. It's trained on M equals to 4 consecutive frames. And the supervision, this is important, it's only on the ground truth frame the supervision is the ground truth from the last one, right? So although we have 4 nets, so technically we supervise on 4, we supervise on 1. This is also because like data sets like Cityscape don't have ground truth for 4 consecutive frames. We do group knowledge distillation. We propose like distillation also on groups of the features, in a way that we transfer knowledge in the full feature space from PSPNet 101, but we also make the information extracted from different paths complementary to one another, right? No redundant. So basically, our loss is basically the cross entropy of the model compared to the ground truth. Then we have the KL divergence between the full feature space and between the teacher and the student, and the KL divergence per group of features, which is basically the third term. So this is a visual representation of our distillation approach. I'm not going to go into much details into this, but as I said just before, teacher, student, we compute the feature for every frame. So Fi is the feature representation of the teacher network for frame 1, Fm is the feature representation of the teacher network for the 4 frames or frame M. Same with the students, but we call them V1 and Vm. Students go through the attention propagation module instead for the teacher, which only sum up the features. And then we have like this green and blue blocks where one belongs to the knowledge distillation of the whole feature set, right? And the other one is like those that are grouped in order, as I said, to make them complementary rather than correlated. So you can see here the results on Cityscape and NYU. We get an MYO of 76.4, 36.2, and when we add overall KD and group KD, we go 0.4 points and 1.2 for NYU depth V2 dataset. Results. Again, you can see our approach compared to others. We can see that it's interestingly like TD2, which means we only to use frame. This is the last row of the table. Achieve better performance, 79.9 MIOU of PSP.NET 101. Right, so we halve the computation basically, and we even get better performance. You can see that the speed in millisecond per frame between PSP.NET 101 and TD PSP50, which is the third to last and last row in the left table. You can see that it goes from 360 to 178. You can also see that LVS has our similar results to PSP18, but again, we take half of the time to do the segmentation. Otherwise, we beat all the fast approaches, and we are also much better than in performance, and we lose of course some accuracy than PSP.NET, except for the big network where, as I said, PSP50 actually achieves better results than PSP.NET 101 at double the speed. More results here. This is an evaluation on Cityscape. In this case, we changed the base network, use BiSnet. Our approach is agnostic to the backbone, right? So it cannot be applied to any backbone. In this case, you know, we compare like BiSnet 34, it actually achieves almost same results, or 0.1 MIO less than BiSnet 101, but it's basically almost 3 times faster, which I also think is a great result. Again, this is not like average, this is average, but it's also like latency, but the maximum latency is not like the one of BiSnet 101. We never run BiSnet 101 to get checkpoint, to get features during inference. We only run BiSnet 34 or 18. Here you can see one qualitative results are beyond the segmentation that, I mean, you can see it's better for what you can, for what it says. It's more like a quantitative analysis that it's interesting what we do. We visualize the attention map in our attention propagation network on the right, and you can see that given a peaks at frame t, which is denoted as a green cross, we backpropagate the correlation scores with affinity matrices, and then we visualize the normalized soft weights as heat maps. So you can see that at t-1 in both cases it seems to focus on the foreground object, t-2 seems to focus on the background, and finally frame t-3 it's kind of dissipated the information. That's maybe why we realized that more than 4 actually network weren't really useful. Some ablation study here, we show the impact of having like a shared subnetwork, meaning all the 4 networks share the same weights compared to independent subnetwork. You know, that's a memory constraint, because like with 4 subnetwork you have to use 4 times the memory to store the networks. But otherwise we found that the independent subnetwork performs better. You can see, for example, here on the left, where we have PSP50 on a single path baseline is 78.2, on a shared baseline it's 8.5, and on an independent, like, which is like TDNet, like for the two different subnetworks, we get 1.4 points more, which is substantial. On the right, you can see we have like the effect of the downsampling. You can just look at the first row, TDP-SP50. We basically get optimal results with 4 subnetworks in terms of trade-off between accuracy and speed. Again, here we have the last ablation study, where we show how the performance decreased with progressively fewer sub-features accumulated. So basically here on the left, it shows that it makes sense to use all the 4 networks, both on Cityscape and NYU. And on the right, to conclude, we show that APM, the attention propagation module, is the more robust module to combine features and to account for misalignment due to interframe motion. And so on the right, we have like the attention propagation, we have the spatial-temporal attention, we have optical flow, and we have just adding. And we see like the performance decrease, like adding is really bad, optical flow improve a bit, spatial attention even more. But anyway, APM is the best, and it's also faster than optical flow and spatial temporal attention. With this one, this is the end of the presentation. I thank you very much for inviting me at the workshop, and have a good day.